which is a not so weak base. It's going to look kind of like a strong base. And we've looked at these. We looked at these Tuesday. And then it turns into HCO3 and adds to the HCO3 that was already there and titrates to the second lowest point. That's the picture we have in this problem. We titrate carbonate to bicarbonate. That adds to the bicarbonate that was already there, and we now have a bigger volume required to titrate both sources of bicarbonate. Does that make sense? Yeah. Okay. So that's what we have. So now I at least know what I have, and I can tell how many moles I have. So this is the moles of the first section. So I'm titrating carbonate. I know, you guys.
Thank you.
I have to sit sideways. Okay, so this goes to HCO3 plus H plus. Now it's going to combine with the bicarbonate that did not titrate in the first step, but now it all titrates here. So in the second step, oh, this is the total. This is the total. So that was the running total. And then the difference between the running total and that is the amount that was just the two sources of bicarbonate. Okay, so the two sources of bicarbonate are this many moles. So how do I find out? No, this was the two sources. Two sources of bicarbonate. And let me get my white up. And so if I take the difference between the total and the part that already titrated once here, then I have just the original bicarbonate. The original bicarbonate. So now I can find my percent weight to weight of each thing. So my moles of CO3 in the original sample we found was 1.71 times 10 to the minus third. That was the first step, carbonate going to bicarbonate. And the mass of that would be those moles times the molar mass. So the mass I got, mass of the original carbonate is those moles times 105.99, and I got 0.1812 grams of sodium carbonate. Okay, so that was the first step. In the second step, I had the moles of bicarbonate original. And how did I get that? I subtracted these moles, or you could do it as volume. Subtract these moles from the total here, and only this could be considered the contribution to bicarbonate that was originally present in your sample. So the moles of the bicarbonate originally present, we got I need my calculator. Because I don't think this calculation is right. 0.02. Okay, so the moles that I get by subtracting this from the total, I get the original, so subtract subtracting the carbonate from the total, subtract carbonate from total, and I get, that gave me 0.1134 grams from 1.35 times 10 to the minus third moles times the molar mass, which is 8401 grams per mole. Okay, so here's the molar mass times the number of moles. Where do these moles come from? Subtracting the carbonate only, the original carbonate, from this total to get the original, from this total to get the original bicarbonate. This is total bicarbonate in this section, and then you could just subtract this from the total bicarbonate to get the original bicarbonate. There it is. So then the weight percent is going to be the mass of carbonate over the original sample mass, which is stated in the problem, 0.5270 grams times 100%. And I got, this is the sodium carbonate, Na2CO3, .39%. In the same way, we could put the original mass of the bicarbonate, percent original bicarbonate, sodium bicarb, is its mass over the total, and I got 21.52%. Those do not add to 100 because the question warns you there may be inert filler. So they don't have to add to 100. Enough of that. So here's a little light oral quiz for you. What are we looking at? What is happening in this titration? What is being titrated and what is the titrant? And how do you know? Weak acid, strong base. This is a weak acid. We're adding strong base. Okay. What's happening? Let's pick another simple one. How about this one? F. Very good. This is my weak base being titrated by strong acid. Now let's pick this one. C. This volume is equal to this volume, and there are two possible answers.
So, like an antipronic base being titrated by a strong acid?
Yes, and we would never pick a weak acid to titrate a weak base. We will deal with that probably next week when we get to stick diagrams, where you have complicated systems with no easy answers. But to titrate a weak base with a weak acid will give you a mixed buffer system at every step, and that's just craziness. And vice versa, a weak acid with a weak base. You just get weird stuff going on, because they're both doing their thing. So there's two possible answers. One is this is a diprotic, let's see, a difunctional weak base. So that's option one, a difunctional weak base that titrates twice to two separate endpoints. So it's got two Ks, and they're separated by 10 to the third, so we see separate equivalence points. Or what's the other possibility?
You have a mixed base system?
Yes, this is base 1, which is stronger than base 2. And they're unrelated. They have their separate Ks, totally unrelated, but it's an equimolar amount. All right, what's this one?
The mixture of weak acid titrated with strong base.
Okay, it's a weak acid out of the starting gate because this curvature here The acid alone cannot hold the pH as a buffer. Once you start making some of its conjugate, you get the nice buffer region that flattens out a little bit. You have more, so X, Y, volumes. X greater than Y means there's more moles of the first acid than there is of the second acid. And this one is weaker. So acid 1 is stronger than 2. Okay? This one is the same thing, only for bases. A weak a weak base here, weak base 1, is stronger than weak base 2. They're unrelated. If they were in the same system, there would be the same volume required step to step to step. The fact that the volumes are different tells you they are different bases. Although we might have something like we just did, where I've got I've got carbonate here that all turns into the difunctional base that all turns into it's amphiprotic, and then there was some of the amphiprotic salt in the mixture, so that was your second base. But those are 2 bases. And then what's happening here? Be careful. The pH is high. It's got a short break. The axis isn't labeled, so we don't know where the equivalence point pH is.
Would that still just be a weak acid with a strong base?
Look at the beginning. This is a strong acid, but it is dilute. Maybe it's 10 to the minus 4th molar, 10 to the minus 5th molar. So this pH is 4 or 5. Doesn't have to be 1 all the time, you know. You make dilute systems. Okay, so that's looking at those. Any questions on that? Okay, I'm going to get a better pen. Where am I? I posted the new notes on the alpha functions. You have this in your, if you have your Canvas site, you have this in a module, and I think it just, I'm going to kind of hit and miss this and then derive the functions for you. So my mass balance equation for a triprotic acid system. So here, this is talking about the total system, the total analytical concentration. This triprotic acid can be the acid only. It can be the first or second amphi. It can be the base only. And those will always add up to the total you put in. If we're just doing acid-base chemistry, we're not doing redox chemistry, we're not destroying compounds and turning them into other things, we're just taking off protons. We're only doing proton transfer reactions, then you always have a total that reflects all the species present in that system. They add up to that total. You can start with any one of them, and they'll all be present to some extent. Let's see. Simply changing the pH, we're just pulling a proton off of a species or putting one onto a species. We're not changing the number of those backbones that are present. They're all in equilibrium with each other. All of their Ks are in force all the time. Here are their Ks, so these Ks are always functioning. And we have this sequence occurring as we move the pH shifted higher or lower. We're favoring one species over another, and that's what we're about to find out. The way we express this is with the fractional distribution functions, which are given here. And each one of them, each species over the total is its fraction. So if 25% of the stuff is fully protonated, then I would get a fraction that would be 0.25. If 50% of it is base, I've got a buffer between this base and its conjugate acid, 50-50 buffer, then each of these alphas would be 0.5. That's what you would calculate. Does that make sense? So how do we calculate these? I put this up for you, but I also brought copies of it to give you. You want copies?